This presentation is delivered by the Stanford Center for Professional Development.
Hey, good afternoon. Okay, so kind of reminding ourselves about a little bit of thinking recursively and where we're trying to work our way toward. Recursive decomposition is really the hard part. Somebody gives you a problem and they say, solve this recursively. Where you're going to spend your time is saying, well, given this problem, how can I find that self-similarity in it? How can I break it apart in such a way that a smaller form of the problem within it, right, if I made that recursive call and then used it, was going to solve the whole problem for me. Maybe there's more than one solved problem. Maybe it's a divide in half, something like that. But that part, right, is usually where you'll spend kind of a lot of your time is trying to figure out how it is you can structure it to divide it in a self-similar way. Once you have kind of that plan about how you're getting a little bit smaller, a little bit simpler, it's usually not so hard to kind of just follow that to the logical conclusion and say, well, if I keep doing that enough times, what do I get to that really will allow me to terminate this, the simplest possible case that all of those minimizing of the problem might eventually lead to something so simple we can directly solve it that we're working toward. Sometimes there's more than one base case, but ideally, right, there's exactly one that everything comes to. It kind of cleans up your code if you can make it come out that way. There's a couple common patterns, and we've seen some of these already, and we're going to see them again and again, but that partly what you're trying to develop is a set of examples you've seen before that help you to kind of use those patterns to explore further problems in the future. And so a very common way of dividing stuff, right, is you have some collection, whether it's a vector or a string or a set of paths or something like that, that part of the recursion often is that you somehow separate one from them. So in the choose problem, when we were trying to choose the people to go to the flicks, right, we picked some student, basically at random, right, and said, okay, this student's either in or out. And so we separated one from the mass, leaving us an n minus 1, and then that n minus 1, right, was that recursive piece about that substructure, saying, well, if I had the answer for the remaining n minus 1, right, I could use the information about this one I've separated out to kind of join it together. So sometimes that's the first person, sometimes that's the last person. In the case of palindromes, it was the first and the last character in the string. Sometimes it's almost a random person, right, that you're picking. But there's the idea of kind of separating one or some small number, leaving the n minus that number to work on. Sometimes it's a bigger chunk. It's a division in half or in thirds or something where I'm dividing and conquering. The binary search doing that, saying we've got some information from the middle that tells us about what these two halves are. And in the case of binary search, we only need to recur on one. We'll see some cases where actually we'll divide it in half and recur on both, but where we're still just dividing the problem into easier, in this case, half as big versions of the same problem that then we can attack recursively. And sometimes there's more like a choice. This is maybe the thematic thing for some of the later things we're going to see today, is that there's some choice of the options that remain. And the recursions, the attack it will take us to make one of those choices, right, which then kind of leads you to a state that has fewer choices to be made, fewer decisions, and allows you to kind of try decisions from there to work your way towards some base case. One of the things I'm also going to be talking about today is some of the implications of the relationship between when you process this part you've separated out and when you make the recursive call. That it's actually totally not irrelevant whether I make the recursive call and then try to process the one, or whether I process it and then do the recursion, that in some situations they'll produce different results and different answers that are interesting to know about how those things play out. So today the theme is procedural recursion, and procedural is differentiated from functional in a very minute, almost semantic bit of semantics about the definition, but it's worth telling you, right, that a functional recursion problem is one that we have a function returning an answer, like is palindrome returning that Boolean true false, the factorial or raised to power telling you what the answer is. In a procedural recursion, we have functions that don't return anything. So there's not an answer being computed in result of that, but there is recursive in calls. So there's a procedure here that calls itself, eventually kind of bottoming out at some base case, and as a result of all that recursion being done, something happens. The one I'm going to do at the beginning here is some drawing pictures, some graphics that draw graphics, fractal graphics, where there's not an answer being computed, but there's something being illustrated on the graphics window. So I'm going to look at two examples of this, because I think sometimes for some students that, the numbers, and the strings aren't the best way to get at this. Sometimes visually, right, really helps to kind of open up the enlightenment for what recursion means in terms of a structure. And we're going to look at some pictures that have a self-similar structure that repeat within itself, that if you look at it at one level of detail, you'll see certain elements that actually, if you look a little closer, you'll see that same element, but just repeated on a smaller scale within that, and then within that, again, kind of moving down to that base case. The way these things will be written in code will be there's some outer fractal that you draw that, as part of its handling, then makes recursive calls to draw these inner, smaller versions of the fractal kind of within itself. Okay, so here is a little bit of code. So I'm not going to tell you what it goes, but we're going to sort of just imagine sort of thinking it through and looking at this to see what kind of things could produce. Draw a fractal. It's given an x, y, and a width and a height, which I will assume is the bounding rectangle of what's being drawn. And then it makes a call to some helper called draw triangle. If I assume that does what it seems like it does, it says, oh, it draws a triangle, right, that's inscribed within that rectangle. Next up, I'm seeing this base case. It's like, well, if that triangle was particularly small, in this case 2/10 of an inch or smaller in either dimension, then we don't do anything further with it. We leave it alone. Otherwise, we do a little bit of computation here, a little bit of math to compute some coordinates, and they're labeled the left, top, and right, which is basically it's making a call on the left sort of sub-region of this rectangle that's at the lower left corner, but half as tall, half as wide. Here's one that starts in the middle and is also half as tall, half as wide, that kind of represents kind of a chunk out of the top, and then one that's to the right. So making 3 recursive calls right on top of that kind of original triangle that was drawn to draw kind of more triangles inside of it. This produces something you've seen before. But you generated a very different way the last time, right? In assignment 1, right, when we had to do the little chaos demonstration, it produced this drawing, which is due to Sierpinski, from a different mechanism, but in fact it is a very recursive drawing when you look at it, right? The idea is there's this outer triangle, and then within it there is a leftmost, a topmost, and a rightmost reproduction kind of the outer triangle at a smaller level of scale. If I look in each of those triangles, right, I see that same self-similarity, right? The lower left of this, the top of this, the right of that, and then similarly looking all the way down. If I just keep going down at each level of scale, I see the same thing, that there's a triangle which itself, right, has these 3 left, right, top regions that exhibit the same structure the outer one did, but just a little bit smaller. Eventually it gets so small that it stops drawing, and that's what terminates our recursion. Let me show you this a little bit with in the compiler, because in particular I want to just talk a little bit about, some of these things I said about rearranging the order of calls and what impact that would have. So what I wrote here was, to try to avoid the math clouding too much of our vision, I kind of just abstracted what the call does. So draw fractal says, well, if it's too small, then it returns. Otherwise, it draws this outer triangle, and then it repeats on the left part of the triangle, the top part of the triangle, and the right part of the triangle. So that's the way it is right now. So this one, in terms of, does it do the work before or after the recursive calls for this particular instance of the problem, it's doing that work before. It's deciding to draw the large triangle, the outer triangle first, and then recursing its way interior to draw the middle parts of the fractal. So if I watch this guy go, I see the big triangle drawn first, right? And then it works its way down the left side, kind of filling that out, which eventually kind of works its way all the way down to the left side and stuff like that. But at each stage, as it gets to the triangle it's starting to work on, it drew its outline first, right? And then worked its way in. So I saw a big triangle, then I saw this big triangle, then this big triangle, then this one, and so on, eventually down to the corner, and then it kind of filled its way back out. So that is one of the aspects where we're looking at, okay, I did the work first. What happens if I turn it around? So I have the same base case, right, and the same order of left, top, right here, but I wait to draw the big triangle until after I've drawn all the other interior fractals. So doing the processing for this one after I've done those. I'm going to get the same picture, but it's going to grow in a different way. That only after it's kind of done the whole thing is the outer triangle, in this case drawn on top, which isn't actually very noticeable because the inner piece has kind of already made up the outer boundaries anyway.
Slower?
Yeah, I slowed this one down a little bit. I'm sorry. Yeah, it isn't any slower in real life. I was kind of screwing with the pausing because I wanted to get it just right, and then one of them I think the pause is slightly faster than the other. So, but growing right from that lower left corner up, then working all the way through the top, and then all the way through the right, and then the outermost sort of thing only being built as kind of an after effect of once the inners have been constructed. So the very first one appearing right way down here. Now let me change my 3 recursive calls. It currently goes left, top, right. I'm going to change the code to go top, left, right. I'll get the same picture, but where is the very first triangle drawn? Is it small or big? It's small. And where does it live within the triangle? The very, very, very top, right? So the topmost point, the top small little triangle that goes there. What is the second triangle that's drawn? The one that's just down to the left of that one. So I should see the topmost one, its leftmost neighbor, and its rightmost neighbor, and then we'll start working our way down from there. That one thing that sometimes is helpful to think about in terms of visualizing what a recursive procedure is doing is to think of it as a kind of an upside down tree where here's my draw fractal to the outer one, and then it makes these calls, right? To top, to left, to right. Realize that the way that the recursion proceeds is that it makes the call to the draw fractal of top, which then makes a call to the draw fractal of its top, which makes the call to the draw fractal of this top, so that it goes deep, right, until it hits that base case. And so this was where I went top, 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 right, to the very topmost one. Well, after it bottoms out here, it comes back to this one that said, okay, well, I drew the little tiny top. Now I need to draw the left and the right. And so the ones that are fleshed out at the bottom here are the left and right of the topmost one. And after those, it kind of comes back. So it will do sort of everything in the top, and the top stop and the top stop and the top stop, before it comes back and starts exploring any of the left and right branches. Once this whole thing has been filled out, so the whole upper third has its fractal drawn, is it going to go down to the left, right? And then again go left, top, 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 right? And then work its way through. So sometimes thinking about it in terms of a tree and realizing, right, that it is not sort of level by level or breadth first. It's not like it draws all the outer ones and then the inner side of that and the inner like that. It really does it all the way down to that base case before it starts unwinding and backing up and revisiting, the pieces that it kind of deferred as part of the recursion to come back to. So the very first call to draw fractal is sitting on the stack frame while these other ones are active, and when they finish their work and unwind, it picks up where it left off in drawing the other 2/3 of the fractal. So this one should grow down from the top, growing the whole sort of top from there, and then it should start to grow the left also from the top, working its way down. And then once it's worked out the whole of the left, do the right also from the top, right, working its way down. So same picture in all of these cases, right? Am I doing the big triangle first, the inner triangles first, the left, the top, the right? But they show you that kind of the processing and how it would evolve, right, is different. In some cases, this is going to really matter to us. It's going to actually change the outcome of the recursion, how we're doing this. So it's good to have a little bit of an idea of how to visualize, right, the different tracing through the calls. Question?
Is it possible to start drawing at 3 different points, like at the same time?
Well, I mean, so technically we have one thread of control, right? And so, at any given point, right, we're doing one thing at a time, right? So really, without more fancy things, the answer is basically no. So I'm going to show you one more little recursive fractal. And this is based on a famous Dutch painter, Mondrian, right, who was alive in the first half of the 20th century there. One of the Cubists is sort of the group he belongs to. And you've probably seen some of these paintings, it might look familiar to you, right, with these kind of very bright primary colors, a lot of horizontal and vertical lines sort of bisecting the canvas, and then kind of some of those squares being filled in with bright colors. This is sort of one of the more famous of the pieces that he did. And his little philosophy I quoted from there, right, was his idea that this is about harmony and beauty, and you can, just through lines and colors, right, produce things that really have an aesthetic component to them. I think it's a pretty neat thing, but I'm not an artist by any means, so I think, well, the solution to that is if I want to create beautiful things, I need to write computer programs that do them for me, because if it was up to me, I won't do it with my own hands. So what I'm going to show you is a technique for thinking of this as a recursive problem. That if you look at what a Mondrian is, if you're sitting down to start this, you have a big canvas in front of you. It starts blank, right? And you say, well, where should I begin? Well, let me just pick a random direction, horizontal or vertical, and then I'll pick a random placement for it. So I decide I'm going to bisect vertically, and I pick a spot somewhere in the middle of the thing, and then I do a bisection of that with my big black line. And now I look at the thing I have left. I've got, well, two smaller canvases, one to the left of the line, one to the right, which themselves, right, I could imagine using that same strategy for. Well, look at it and decide whether to make a horizontal or a vertical line. And then occasionally along the way decide to throw in a little color. So when I have a canvas, maybe wash it in red or blue before I go through my division. And sometimes I decide not to divide it at all. I'll get to this portion, for example, this canvas that I've sectioned off here, and I might decide to just leave it there and say, okay, well, that's good enough. I don't want to go any further on that one. Oops, that's not what I wanted to do. And so it has these three options. Divide the canvas horizontally, divide it vertically, do nothing. And then when I have those two smaller canvases, right, I recursively can apply the same kind of Mondrian style effect to it. And when I get to something that's too small, I can stop trying to divide it further. So I'll show you what the code looks like here, and then I'll show it running to you. Most of it actually is a little bit gunky just because there's a little bit of math of adding and moving and stuff like that around. But it has this idea of, oh, here's the rectangle you're trying to draw a Mondrian in. If it's too small, so in this case, anything under an inch, I decided was too small. Otherwise, I fill the rectangle with a random color, which often is white, sometimes yellow, sometimes blue. And then based on three cases of a random choice, I either decide to just leave it as is, filled with whatever color I chose, or I make a line vertically in this case, or horizontally in that case, and then recursively section off the two portions I've made to recursively apply draw Mondrian to draw some more Mondrian in those pieces. Does it work? And by work, I mean the code works. But does it actually produce art? You can be the judge. Oops, that was not the right one. I just ran Sierpinski, and that won't do. Okay. Well, but the good thing is, see, it's easy to make new ones if you don't like that one. I don't like that one either. Too much blue. Well, that's kind of getting somewhere. I might put that on my wall. And then at this point, I just started making them like, just as many as you want. Just keep going. See, some of them, it stops early. It has nothing to do. My mother-in-law is an artist, and I have to feel like I apologize to her whenever I do this, because I think I'm really not trying to make fun of art as though actually a computer can do anything. The truth is, when you do this, actually what you realize is that it's not art, right? That what's truly aesthetic is something that actually is not generated by randomness and recursion. But it's still interesting how it produces things that actually kind of have that pattern to them that are sort of Mondrian-esque, just by simply kind of taking this recursive strategy to saying, well, that's a little Mondrian, this is a little Mondrian, and if you've assembled them all together, you've built a big Mondrian. Millions of dollars right there I'm generating. I'm telling you, when I retire from teaching, that's going to be my next career. Turning out fake Mondrians. All right. So any questions about little pictures and graphics and things?
On the previous one, could you go over like what's passed in each of the curses? When you recall, draw a Mondrian?
Yeah, so the only thing it takes is, it's just a rectangle. It says, this rectangle you should fill with Mondrian-like things. And so the outer rectangle is the whole canvas. And then once I've done a bisection, right, I've picked some point in the middle. I've divided the rectangle into two smaller rectangles, the left and the right, not quite halves. It depends on, it's not necessarily exactly half, but I have one that starts in the origin and goes to the midpoint, one that starts at the midpoint and goes to the right side. And so it's just basically taking the outer rectangle, dividing it. If I drew a picture here, it might help. You've got this thing, you choose to bisect this way, and so what you're passing is this rectangle and that rectangle. And when this one decides, let's say, to bisect this way, then it'll pass this rectangle and that rectangle. And so at each stage, you have these smaller rectangles, right, that were pieces of the outer rectangle that you're continuing to draw Mondrian into. Eventually, they get so small that you say, I won't further divide that up anymore. I'll just stop right here. And so the line actually is drawn on the way down, it turns out. If you'll notice, the draw black line happens before it draws the thing. So I'll draw the line and then draw, like a background on top around it and stuff. Either way, it doesn't actually really matter. If you could draw it on the way out, and you'd end up with the same picture as whether you draw it on the way in. It would appear differently. On the back.
Can you explain why you have it return instead of doing like a break or some other means?
Well, in general, I just need something that says, don't go through the rest of this code. And so the alternative, right, one easy way to flip this around. So a break, right, will only be useful in the context of a loop, right? I'm not trying to get out of a loop or a switch statement, right? So if I really want to leave the function, return is the quickest way to do that. The alternative is I could have inverted the sense of this test and said, well, if it's at least an inch wide and an inch tall, then get into this code. And then it effectively would say, well, if and it didn't pass, it would end up kind of dropping to the bottom and falling off. But either way, right? So I think probably I tend to prefer to do it this way just because I like to get my base case up from the front of my eyes, seeing what it does. And typically the right thing for the base case to do is identify that you're at the base case, do whatever simple processing is required in that case, and then return the answer or just return right away saying, I've handled the base case, and now let the rest of the code be, and now in the recursive case, go on. This all could have been in an else, for example, and it wouldn't change things, so the control flow is still the same. But that's very much the style I tend to use is, if we're at the base case, do the base case stuff and return. Now I'm going to hit you with the most classic recursion example known to all CS students worldwide. That I wouldn't be doing my duty if I didn't teach you a little bit about the legend of Brahma and its towers and how relevant it is in today's world that you know how to move graduated disks around. All right, so I'll give you the setup. Apparently there are these monks. And there's a legend of the Tower of Brahma that these monks, apparently big troublemakers, monks, you know how they are. You got to keep them out of trouble. So the deity here had this idea. It's like, well, I'm going to give them this task that's going to keep them busy for a long time. And that way they won't be, causing problems. So what he did was he stacked up these three spindles, A, B, and C, big poles. And he had these big, heavy discs. They're made of solid gold, apparently, in the Brahmin religion. And they are graduated. So there's a big disk at the bottom and a slightly smaller one on top of it, and so on. And they're all stacked up, let's say, on tower A. I've labeled them A, B, and C just to keep track of which is which. And the deity says, yeah, I got all these disks all stacked up on this tower in A, but it turns out I'd really much rather have them on tower B. Sorry, what can I do? I accidentally put them there, and of course I'm so strong and big and heavy I could move them. You, on the other hand, right, puny little human beings that you are restricted to being able to only move one disk at a time because they're so inordinately heavy that it takes kind of everybody's strength to move just even the smallest of the disks from one place to another. And he further instates these rules that the disks all have to kind of live on a spindle, so you can't actually just pick them up and start throwing them around in the desert. You're trying to move this whole tower from A to B. You can move one at a time. And in addition, because they are so heavy, if you were ever to put a small disk down on a spindle and put a larger disk on top of it, any of the larger disks, right, it would immediately crush the one underneath it. And so that's disallowed as well. So you always have to kind of keep an ordering of large ones on the bottom to smaller ones on the top. All right, that's the deal. That's the setup. Those troublemaking monks. Apparently there's 64 of these things too, so 64 of these guys to move. All right, in computer science, I don't have any solid gold heavy disks, but I do have some very brightly colored plastic disks. And so really this is actually not so much the towers of Brahma or the towers of Hanoi. It changed location somewhere along the point in history. This is the towers of Fisher-Price. I did not actually steal these from my children, but they have one at home, which I keep waiting to see them show evidence of their recursive mastery on, and I have to say, very, very disappointing. Okay, so I've got a tower in this case of 6. This is A, this is B, this is C. And I want to get this from here to here, and I don't want to violate all those rules. I can't just start throwing the disks around and making a mess. It's like, if I'm taking this guy, it can move from here to here, so I don't have a lot of choices here. But once it's there, for example, this yellow guy can't go on top of it because it would squash it, right? So I can kind of move the yellow one there. So there's something a little bit about this idea that somehow there's going to have to be some back and forth, right, that is a part of what's going on. So let's go back and look at this for a second. So as I said, many of your classic recursive patterns involve sort of looking at the problem you have at hand and trying to decide, well, is there some way you could separate it a little bit? And one of the more likely ways to do it is say, well, can I somehow move one disk out of the way, leaving n minus 1 that could be worked on recursively? Okay, so it's probably not likely that I'm going to be able to get, let's say, the blue disk out of the middle very easily. So it seems like probably the two most likely candidates for that are either the topmost disk somehow gets moved out of the way to uncover the bottom part, or the bottommost one, somehow I get this other tower out of the way. So let's start by thinking about the top one, because that's certainly the easiest. I can get this top guy, as I said, and stick it somewhere. Well, let's say I put it over here in the temporary one. Okay, I get it out of the way. I now have a tower of n minus 1 left. Okay, that seems, like it's kind of getting me somewhere. But now I need to move that tower of n minus 1, kind of over here. But the situation I've made is I've actually made the problem not easier in this situation. It's a little bit smaller, but it's actually further complicated by the fact that given this small disk is over here occupying the small spindle, means that suddenly this spindle is kind of out of commission. For the purpose of moving this tower, this spindle might as well not exist, right? Because this guy's blocking anybody from getting there. So it seems like that I have a problem that looks kind of like the one I started with, but it's not actually any easier. In fact, it actually got a little bit harder. So let me back up from that. Let me just let that be a dead end for now. And I'd say, well, what about this purple disk that's down here on the bottom? I'd like to get to the purple disk. Well, I can't just pick up the whole tower and move it. Or can I? Well, let's think. I've got this tower of n minus 1 on top of the purple tower. If I were able to produce a delegate, a clone, a coworker, right, who I could say, hey, by the way, you know how to move towers. Could you please move the n minus 1 disks that are on top of the purple one over to the temporary spindle using this other one as the spare? Well, that's kind of interesting. So if that would work, if somebody would come along and spirit these out of the way, and in doing so, right, while they're moving, right, this purple disk can remain on the original A spindle without actually any interference. Since it's the biggest, all the things can go on top of it, so it doesn't matter that it's there. It's not interfering with the operation of what's going on. So if I could move that n minus 1 out of my way and kind of over to that temporary spindle, then it would uncover this bottommost one, which then is one step away from where it wants to be. It wants to move to the middle. And then that same schmuck I got to do the work for me here, where I said, please move my tower out of the way, can be kind of pressed back into service while I'd say, oh, by the way, I was wrong about that. You know that big tower you just moved full of heavy things? That wasn't where I wanted it. Could you move it actually from where it is to the place where the purple one is now, back to the destination? And again, right, I've got a tower to move, and I've got a purple one laying on one of the disks, which is bigger than everything in this tower, so it's actually not interfering. And then if it kind of does its work, using this one and back and forth, if it did what it was supposed to do, then I did move my tower of height 6 from here to there, while seemingly doing no work. Like the only thing I did, right, was recursively. So this is really where recursion's kind of buying us a lot of the heavy lifting. I want to get this tower from here to there. There's all these rules. It's very complicated. I can't think about it. It makes my head hurt. But if I just believed that I was in the midst of solving this problem that I haven't yet solved, and if I had that solution and I believed and I had faith, right, and I believe that it will work, I move these guys out of the way. I move this over here. I move it back. So let's see how much I can do without blowing it. So really what it comes down to is that moving this one out of the way really starts by saying, oh, well, what I first need to do is move these 4 guys off the top of this. And then to move these 4 guys, I was like, well, I need to move these guys off of that, which eventually kind of comes down to something so simple, right, of moving kind of that single disk that I can move this here, move that there, move that there, move my green one, move my orange one, move my yellow one, move my this one. Oh, we're getting somewhere. Now I have to think. Yeah. There's a trick to how I'm moving my hands that actually is wrong. Yeah, voila. All right, all done. All done. Don't ask to see it again. Can't be done again. So here, I'll show you a little code. I'll show you the code. Tiny little piece of code, right, that solves the whole problem. I've got a parameter coming in here, which is the height of the tower to move, and then I'm identifying the source, destination, the temp, the 3 spindles that are currently in play here with these letters, characters. If there's something to move, so I'm going to talk about the base case in a second, but in the general case where I've got 5 things to move, it says, well, move the 4 disks that are on the source. So the source, let's say, is A in this case. And now instead of moving them to the destination, move them aside to the temporary spindle using the destination as the temporary. Once you've gotten those out of the way, you move that single disk, the bottommost disk from the source to the destination, and then you go pick up that n-1 tower you left on temp and stack it on top of you on the destination, now using the source as your temporary. At any given stage, you've got 3 to go, then you've got to move the tower of height 2 off of you. When you've got 2 to go, you've got to move the tower of height 1 off you. What a base case you could imagine being pretty easy would be, well, a single height tower, just one disk, right, can be exactly moved. This actually prefers going to even a simpler case, right, which is if you're asking to move a 0 height tower, there's nothing to do. So in effect, the base case for the 0 is if n equals 0, do nothing for any positive number, and then it goes through the process of shuffling the ones off of you to uncover your bottommost disk and then moving them back on. So 5 little lines and all the power in the world. Question?
Why not? Why use the destination as a temporary?
Because we plan on, so the idea is that if we're moving here from A to B, right, I need to leave this one open, right, so that I'll be able to move the purple one when the time comes. So it's actually, I'm trying to move this out of the way, right, and so here's where it's trying to go. And in the process, right, you have these 2 places you can kind of shuffling back and forth, where they came from, where they're not going, and where they are going. So the kind of decision about where you, so there's always the source and destination are pretty obvious, and then what happens is whatever's left over is the one that gets used as the temp.
Why can't you put those on the second one?
Well, if I put them on the second one, how am I going to get the purple one underneath them?
Well, you wanted to put on the last one.
Well, my plan was to move from A to B, actually. It doesn't really matter. It's totally,
okay.
you know, but I'm trying to move from A to B, so in fact, C is like the place where I'm just leaving stuff temporarily.
Okay.
So either way, so the idea is that if you're moving from A to B, then it's always the one that's left out that becomes the temporary holding bin as you're moving them around. So now that, of course, I can't do it, but I can make my computer do it. Because the answer to things is not to learn how to do stuff, it's to actually write computer programs to do stuff for you. So we got a little bit of code here, and I'm going to put it into trace mode, and I'm going to actually slow it way down. Let me go back and start it again. And so I'm going to let it go, and it's going to do these stack frames, and you'll see, well, if it has a tower of height 4 to move the 3 across, move the 2 across, move the 1 across, move the 0 across, and that will cause it to start doing its unwind. Now it just moved the 1 height tower over to C, and then comes back to, and so you're going to see that the stack frames here show how deep the recursion ever gets at any given point, right? In this case, having 4 disks, it gets about 4 deep, actually 5 because it goes to the 0 case. And that you'll see it kind of go down and back as it shows it kind of moving the tower away and then getting back to moving the bottommost disk and then doing another deep recursion to move that tower back on top. And so at any given stage, right, they're all stacked up with their, and the start, finish, and temp start switching positions, right, depending on kind of what level of the recursion we're at. Each time we get to 0, we hit our base case and unwind. Let me make it go a little bit faster because it's a little, I surely can. Right. And so it just moved the tower of height 3 all the way away, and now it's moved the bottommost one back, and now it's going to start moving the tower that was shuffled away out of the back onto it, and then eventually kind of stack it back up onto the B where it wants to go. I can make it a little bit taller.
64.
Yeah, 64. We'll talk a little bit about why I wouldn't want to put in the number 64. You can see it kind of moving them around, dancing, much better than I would do. Actually maintaining the rules at all times. You notice no disk getting smashed. I go up to 6, right? And so So never getting lost, always keeping track of what it's up to, right? It's a very tricky thing for a human to do, but a very easy thing for a computer, right? To be identifying what part of the recursion we're at and what we're trying to do right now without getting confused about the other things that are also kind of ongoing. They're all very neatly kept apart. You notice it starts to take a little bit longer, right? As I added a disk to that, it seems like it got quite a bit longer. How much longer? If it took, a minute to do 5 of them, how long is it going to take to do 6 of them? 2 minutes. Why 2? Help me out.
It's like it's doing that whole thing once with -1, and then it's doing I don't know how to explain it really well.
Yeah, no, you've got exactly the right idea, right? It's like, so if I have a 5-height tower and I want to move it to here, it takes a certain amount of time. All this shuffling happens, that took a minute, now it's there. Okay, so we know that. If I add this disk at the bottom here, then I'm going to move this 5-height tower over here, so that took a minute, right? I move this disk, that's assuming that that was free, right? And then I have to move this whole disk back. So each time I add one more disk, it takes twice as long as it did before. If it took 5 minutes, it's going to take 10 minutes. And if it took 10 minutes, it's going to take 20 minutes. So every single disk doubles, right, the time that's taking. Well, doubling is a pretty fast-growing function, right, exponential, right, so that, 2 to the 32nd is 4 billion, right? 2 to the 64, I don't even know the names for. And so the sort of legend of Brahma says that when the monks finish their task, they get all 64 of the disks from A to B, right, the world is going to end. And the question is, do we need to be worried? I think not. But in fact, if they were actually just getting close, like let's imagine you saw those monks and you're like, oh my gosh, they're like on the 62nd disc. Oh, any minute now. So while they're not looking, go slip a 65th disc under there. The universe just got twice as much lifetime. Right? They won't notice. Those monks. They're always like drunk and whatnot. I mean, if you had to move towers all day, you'd need something. All right, so that's so it's computer scientists, for some reason it moves to Vietnam, and it's called the Towers of Hanoi. But when people will ask you about recursion, everyone will want to know, have you been exposed to the towers problem? And now you have, we'll say. So very powerful little piece of code, right? And that feels very much like a trick. I can remember sitting in a room not unlike yourselves a gazillion years ago, and having someone explain the Towers of Hanoi to me and just not believing it, right? Just, like saying that just can't work. You didn't do anything, right? All you did was call yourself before you were even done, and that's just nonsense, and that's just not right. And then after some amount of thinking about it and working it through, I did conclude that it actually did work, but at first it really did seem like a trick. So if you're feeling that way, this is kind of like par for the course, that it is a little wacky to get your head around, but it is sort of relying on this idea of the mathematical induction. If you can do it for this smaller version of the problem and then build on that to solve the bigger problem, as long as you make that logical progression from this problem to the smaller one down to that simple case, you will eventually solve the whole thing.
What's DST?
Destination in this case, source, destination, temp. Okay. So then there are two problems I want to do, and I'm probably only going to do one today, and I'll do one on Friday, that are what I think of as kind of the mother problems of all recursion. That many problems, in the end, just boil down to an instance of either the permutation problem or the subset problem. And so I'm going to show you permutations and subsets both kind of in gory detail, and then I'll try to kind of build with you a little bit about how many things actually just are a permutation problem or a subset problem when looked at the right way. And so once you kind of have these two in your arsenal, you're very much prepared to attack a lot of different recursive things using those same patterns. So what I'm looking at here is permutations. You have an input string, let's say it's the alphabet, A through Z, 26 letters. What you'd like to do is enumerate or print or list all of the ways you can permute the alphabet. So there's 26 letters in the alphabet. If you know anything about combinations and permutations, you realize there's 26 ways you can choose the first letters, A, B, C, D, all the way to Z. And then that leaves you with 25 letters from which to pick the next one, right? So there's 25 ways to do that, and then 24 ways to pick after that. And so at each step, right, you have kind of one fewer choices remaining to conclude the permutation. And that the number of permutations is then factorial in the length of the input, so 26 factorial, which is an enormous number. Tells you about all the different ways you could rearrange the alphabet. For a smaller string, A, B, C, right, there is 3 factorial for that, 6 different ways, right, that you can permute that. But the same principle applies no matter how large the string is. Okay, so our goal is to write a function that, given an input string, will print all of the permutations of that string. That's the goal. Okay. So I've got ABCD coming in. I want to be able to print DCBA and CABD and ABCD and ABDC and all these other variations. That I'm going to use the strategy that actually I described just the way I did kind of intuitively about how permutations are constructed. that at any given point, right, I have a choice to make, and that choice in this case will be what's the next letter to attach to the permutation. So if I imagine my goal is to build the permutation up one letter at a time, I start with an empty string, so I'm going to have the input and the output, I'm going to call it. The input is the letters I haven't yet used, so in the case of the string ABC, it might be the whole string ABC. I've got this output, which is what letters I've chosen so far. It starts empty. I look at my ABC and I say, well, each of those letters could be the next one that's here. Why don't I go ahead and pick one, pick A for that matter, right? Put it on the output, and then recursively call myself to say, well, given A is in the front, could you also print all the things that you can permute the remaining letters, B, C, behind it? And after that's kind of, through the magic of recursion, done what it's needed to do, I can come back to the call I was at and say, okay, and now it turns out, well, it's not just A in the front I need to try, I also need to try B in the front. So I try B in the front and now permute the AC that I leave behind. I try C in the front and permute the AB that's left behind. So at any given stage of this recursion, right, I have these options which are of all the letters remaining in the input, each of them needs to be tried as the next one to go. And then I need to recursively permute on this slightly smaller form of the same problem, right, where the output is one shorter, right, I've removed one letter from consideration because I've picked it, and the input is one longer. So at each level of the recursion, it's like one letter is shuffled from the output to the input. After I've done that n times, right, I will have created a permutation, then I can just print it, and I'm done. And if I do that through all the patterns, I'll get everywhere. The options, right, that I'm exploring are the letters, right, and then there's this base case, well, when do I run out of things to do? It's when I've assembled a whole permutation when the output is empty and the input is full, let's say. So I talked about this. Let me just show you the code, because I think that is where we can spend the most time trying to illuminate what's going on. So here's recursive permute. The form that I'm going to use here is going to take two arguments, which is I'm going to explain the need for in a second, but largely what I'm going to be tracking is that input and output. What I have assembled so far is in that first parameter, so the things I have committed in the permutation I'm building right now. The rest is those letters that haven't yet been chosen, that have been passed over so far, that are remaining to be permuted and attached onto so far. If the rest is empty, that means everything has been attached into so far. I have a permutation, and then I just print it. If it's not empty, so in my else case, then for every letter that remains in the rest, so imagine for example, I'm starting with the whole alphabet at the very beginning and so far was empty, this for loop is going to iterate 26 times. It's going to take out the ith character, and it's going to append it to the permutation, and then it's going to remove it from the rest to have kind of show that it's been used, so we won't accidentally repeat it later in the permutation. And then we make this recursive call saying, okay, now having picked the letter M and put it in the front, here's the whole alphabet without M. On a subsequent iteration, it'll be like, well, here's the whole alphabet without K, and now I added K to there. Then we're going to do this once for every possible letter that we have. We're choosing it once and then making the recursive call to say, and now just magically deal with exploring all the possibilities that follow from this one. Eventually, right, that rest. So every single call, if you look at the arguments going into the recursive call from here, next and remaining, this is always one character longer than so far, and this is always one character shorter than rest. And so in terms of this tree of recursive calls, we have, some things to pick from. So at the beginning, right, we have everything in the input, nothing in the output. Well, once we pick something, right, that shuffles one character from here to there, a subsequent call down here moves another character, and then eventually we've emptied out the rest. There are other alternatives, though. For example, up here, right, it could be that we picked B and left behind AC. It could be that we picked C and left behind AB. That before it's all done, we're going to have to try all of those things. And so the very first level of the recursion is going to make a number of calls equal to the length of the input. Each subsequent level, right, in here makes one fewer call at each branch. So if I had a 26 at the top, each of those 26 then makes a 25 underneath. So there's kind of 26 25s branching down there, and each of those 25s makes a 24. So this is an enormously wide tree. The depth is bounded by the total number of characters, but very, very wide. And I'm going to come back and then just think about this, but I'm just going to show you a little part of the tree to get an idea. If I'm permuting A, B, C, D in the so far, sort of the input, the permutation we have so far starts empty, and there are 4 calls that are being made, first with A, then with B, then with C, then with D, in each case removing that letter from what remains and then exploring. So if I kind of further expand this call, it makes 3 calls, right? One having pulled B to attach on, one having attached C on, and one having attached D on, leaving the remaining 2 characters. And then underneath that, right, picking that 3rd character, and then eventually picking the 4th character, which there's no choices there. So this is only a partial part of the tree, but it gives you an idea of kind of what the shape of that recursion looks like. And knowing that thing we talked about with the Sierpinski should help you to visualize what's the first one printed, right, is that it goes deep. It picks A, and it says, I'll print everything that starts with A. And that means I'll pick everything that starts with AB and ABC. So the first one printed in this case is the ABC. I'll see all the permutations that begin with A before it completes this whole arm. And then as the recursion unwinds back and saying, I've explored everything that you could permute B, C, D into, then it will revisit that earlier decision and say, now let's go again, trying it with B. So we'll see all the permutations that start with B printed in sequence next. And then we'll see all of C and then all of D. This is a tricky thing to get your head around, but it is a critical pattern to get in your arsenal so you know how to apply it. So what this is kind of that choice pattern, right? It's like, of the choices I have, I need to go through the process of making those choices, updating my state to show that choice has been made, and then recursing from there, making that recursive call to kind of further explore whatever choices remain, having made this one, which causes there to be 1 fewer choices to make. In a permutation, you have to make 26 choices, right, for the alphabet. Well, you make 1, and then you have 25 to go. You make 1, you have 24 to go. Each of those calls, right, is working its way down. There's one little detail I'll mention, then we'll finish this on Friday, which is that probably the way this function would be presented to a client or a user who wanted to get the permutations is it makes more sense for them to say, here's the string I have, could you please just list the permutations? This notion that somehow I need to track what I've generated so far is very much an internal housekeeping part. And so in effect, list permutations is likely to look like this, and then just immediately turn around and make a call to the real recursive function that set up the state, the housekeeping that was being tracked through it. And so we'll call this thing a wrapper function. That all it is 1 line of code that just sets up the right state to get the recursion going and kind of state managed. We will see that quite a lot, actually, in a lot of code, so just know about it. Come Friday, we'll talk about subsets, and then we'll start looking at recursive backtracking.